Okay, here we're going to continue our discussion from the last lecture about how to determine enthalpy when heat capacity is not a constant. We talked about finding a web page. I found that web page. Here it is, the National Institute of Standards and Technology, abbreviated NIST. This is a government-funded website. Our tax dollars go into this. And what it gives is a collection, this particular one, the NIST Chemistry Web Book, gives a collection of physical data, thermodynamic data, and a bunch of other things for various chemicals. But first, just let's review where we're going here. All right, we said that enthalpy, the change in enthalpy, can be calculated as the integral of the heat capacity at, say, constant pressure times dt, where here we're going from temperature 1 to temperature 2, or the change in internal energy delta U is equal to the integral from an initial temperature to a final temperature of the heat capacity at constant volume times dt. And if heat capacities here are not constant, you can't pull them out of the integral. In fact, you have to know how heat capacity depends on temperature. And that's where the NIST website comes in handy. All right, let's check this out here. Have a slow internet connection at home. Here we go, the NIST Chemistry Web Book. And what we can do is search. Let's search by formula. And let's enter in, say, CH4. So we're going to get some data for methane. And let's say, let's get some gas phase thermodynamic data for methane. Oh, look, you can get all these things too. IR spectrum, NMR spectrum, and so on. But we're just looking at thermodynamic data. And here we go. Press here to search. So we're going to search, see what we get. So, well, look at that. The molecular weight, or more properly called the molar mass, the UAC or IUPAC standard name, and all this stuff. Look at that. Ooh, chemical structure. There's methane. Information on this page, gas phase thermochemistry data, etc., other available data, and so on. So we just keep going down here. Oh, gas phase thermochemistry data. Keep going here. Oh, there's the standard enthalpy of formation of the gas. Various values here. We're looking at what we want to find in here is the temperature dependence of heat capacity. So we'll go down here. Constant pressure, all this data. Look at that. Our tax dollars really were well spent, maybe. Here we go. Gas phase heat capacity data. This is called the Chem351Fall equation. This is the heat capacity at constant pressure, so Cp. This is how it depends on temperature. A, constant, plus another constant times T. This T means temperature, plus Ct squared, plus dt cubed, plus E divided by T squared. So this looks like a power series expansion of heat capacity in temperature. All right, so there it is. So there's the heat capacity. So let's remember that. And go back here, we're going to do a delta H. So delta H will be the integral from one temperature to another temperature of the heat capacity at constant pressure from the Chem351Fall equation. That's A plus BT plus CT squared plus DT plus E over, what was that, T squared? We'll just check that. And plus, minus E over T. So that should be minus, let's just see here, minus E over T, just E over T, times dt. All right, and you're saying, well, what about these other things here? Well, yeah, clearly I'm using the wrong one. It's late at night. I have no life here. It's Labor Day. So let me just repeat this. This is plus ET squared. Yeah, okay, plus ET squared. There we go. That's the right equation, dt. So we just put in heat capacity, what this is. So where did this equation come from? Well, this is an empirical equation, and the parameters A, B, C, D, and E are empirically determined, and here they are. For different temperature ranges, here's the A, B, C, D, E, there they are, for this temperature range, and then for this temperature range. All right, so there's that expression. We know what A, B, C, D is, put in there, and we integrate this. Let's just go ahead and integrate this. This would be AT evaluated between T1 and T2 plus BT squared over 2. That's the integral of BT. Again, evaluated from T1 to T2. Plus, let's integrate this. This will be CT cubed over 3, evaluated between T1 and T2. CD, that should be DT cubed, I bet. I'm going to check that. Yes, DT cubed. I forgot the cube there. So this will be DT to the 4th divided by 4 times evaluated between T1 and T2. And this final term here, that's the E over T squared, and you integrate this, you get a minus E over T evaluated, yeah, that's right, from T1 to T2. All right, so that's what that is, and remember how to do the integral. The integral, let's just do this. This would be AT2 minus AT1 and plus and so on. So you evaluate this expression for T2 and then subtract it for the expression for T1. All right, but let's go further. Let's totally geek out here and actually calculate this. So we have the expressions A, B, C, D, and E. Let's, for fun, we're going to put this in an Excel spreadsheet. There we go. I'm going to copy this, and then we'll go to an Excel spreadsheet. We'll put them right there. We'll put them right there. Yeah, hello. There we go. There they are. Let's paint this, make it look nicer. There we go. So there's our data, and now what we want to do is to go ahead and make these evaluations here so we know what A through E are. And okay, so, and we have to have two terms. This will be T2 and T1. So what are we going to integrate this? Let's go from, say, 300 to 400K. So this will be T1. Let's just label it up here, T1. And this will be T2. Okay. So there we go. Those are limits of integration. So let's write down terms for, say, A, B, C, D, and E. So this A term, this will be equal to, let's go back here, A T2 and A T1. So that would be equal to A. And I can put dollar signs around there because I'm going to copy them down over here. Times, so that's A times T. Okay, so that'll be A times T1. But I think I noticed something here. Let's go back to that web page and go back up here. Look, T in this equation here, those T's are temperature in Kelvin divided by 1,000. Now, why would they divide by 1,000? I don't know. These are government scientists. Who knows what they're doing? But so it looks like the temperatures in this expression, and therefore the temperatures in this expression here has to be Kelvin divided by 1,000. All right, so this would be, if you take 300 and divide by 1,000, we get 0.3. and 400 divided by 1,000 is 0.4. So we'll properly label these. This is T1 divided by 1,000, and this will be T2 divided by 1,000. And those are the numbers we have to put in there. All right, so there is A times T. Good. This will be equal to B times T1 squared divided by 2. Remember, I'll just go check that. So this is BT squared over 2, evaluating T2 and T1 and T2. So, let's put dollar signs around this one here. All right, that looks good. This is equal to C, which is that, times T cubed, raise this to the third power, divided by 3. Okay, so what we're doing is putting this, CT cubed divided by 3, evaluated T1. Okay, that looks good. This one will be equal to D times T1 raised to the fourth power divided by 4. And this will be equal to minus E divided by T. All right, it's minus E divided by T, evaluate T1. Okay, and let's put some dollar signs around this. Okay, so there we go. That looks okay. This is not, is this right? No, there we go. That's right. So B3 is B times T cubed, or T squared divided by 2. That's right. So I'm just checking the ones up here. So that should be B6, B5, B4, B3, B2, B1. And this should be B8, 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 B8. Okay, that looks good. Now we're just going to copy these over here. And the ones that we put dollar signs around didn't change when you copied them. However, this one, B8, is now changed to C8, which is up here for T2. So here are the terms evaluated at T1. Here are the terms evaluated at T2. And what we want to calculate is the terms evaluated at T2 minus those evaluated at T1. All right, so this will be equal to, well, the terms evaluated at T2 minus those evaluated at T1. There's that. So we'll now drag this down. There it is. And then finally, we have to add up all these terms, that plus that plus that plus that plus that. So here, we'll put the sum, or we'll call the sum will be now the integral. All right, that'll be equal to the sum of these numbers. All right, so there it is. That's the integral of the heat capacity evaluated over T. And let's go back to the web page, see what units those are. CP is the heat capacity in joule per mole Kelvin, and we're multiplying it by Kelvin, so this is joule per mole. Okay, so joule per mole. There we have it. So this is the enthalpy change in taking methane from 300 Kelvin to 400 Kelvin, gas phase change. And what we've used here is the temperature dependence of heat capacity to integrate that. All right, so that's it. I hope you had fun doing that calculation. The next lecture will be more about enthalpy and internal energy. This is internal energy up here. Okay, see ya.